Dynamic management of aircraft configuration and route structures. DYN-MARS is a SESAR initiative focused on the dynamic management of aircraft configuration and route structures. The project addresses a critical challenge in modern aviation, reducing environmental impact during descent and approach through smarter, more flexible system design and improved energy management. The challenges: descent and approach phases are often louder and less fuel efficient than operationally necessary. This is partly due to fixed procedures and static routes that don't account for real-time conditions, and partly due to uncertainty in aircraft trajectory prediction. As a result, configuration changes like deploying flaps or landing gear often happen too early, increasing drag, noise, and fuel consumption. The blockers. Two major barriers limit improvement: procedural constraints, where standard operations restrict required flexibility, and missing technical capabilities, where neither air nor ground systems are fully equipped to manage aircraft energy dynamically. DYN-MARS tackles both, aiming to create a seamless, optimized descent operation. A three-level approach. DYN-MARS provides a coordinated, three-level solution. Each level targets a key aspect of descent management, from how the routes are structured, the aircraft are configured, or information is exchanged, to how the data is used. Level 1. Dynamic route structures. The first level rethinks airspace design. Dynamic route structures allow for real-time adaptation of arrival paths based on current traffic density and runway demand. This flexibility helps aircraft remain higher for longer, reducing noise disturbance on the ground and improving energy efficiency by better predicting their remaining flight trajectory. Level 2. Augmented data exchange and energy management. The second level focuses on smarter decision-making. Augmented data exchange ensures that energy-relevant information is shared between aircraft and ATC, supporting informed, synchronized decisions. This real-time coordination is essential for managing descent as a shared process, not just an individual flight task. Level 3. Enhanced avionics and updated ATC procedures. Avionics enhancements enable aircraft to dynamically predict the best timing for flap and landing gear deployment. Meanwhile, updated ATC procedures support more targeted, minimal speed interventions. This reduces the uncertainty on the aircraft side and hence the number of level-offs with additional engine thrust during descent and approach, and lowers fuel burn. DYN-MARS integrates flexible route design, adaptive aircraft configuration, and shared situational awareness. By managing aircraft energy dynamically within a coordinated system, it enables quieter, more fuel-efficient descents, without compromising safety or throughput. The DYN-MARS solution concept. As an aircraft nears its destination, the descent phase becomes a precisely coordinated exchange of information between air traffic control and the flight crew. A central interface in this process is the Flight Management System, FMS, which manages both the lateral and vertical trajectories. Throughout the descent, uncertainty in the flight path is progressively reduced. The information exchange begins prior to descent initiation. Accurate wind data is essential for computing an optimal descent profile. To support this, high-resolution weather model data is uplinked to the aircraft's FMS. In the next step, Air Traffic Control (ATC) selects the currently active arrival route from the predefined set of available route structures and assigns this route to the aircraft. As a response, the flight crew activates the arrival route from the aircraft's pre-coded navigation database, prompting the Flight Management System (FMS) to generate the initial vertical flight profile. Next, based on the previously assigned arrival route, ATC provides the expected shortcut and any applicable speed restrictions. Information about expected lateral shortcuts along the published arrival route allows the FMS to further optimize the aircraft's energy state by accounting for the remaining flight distance to the airport. In addition, estimated times over each waypoint can be calculated and transmitted to ATC via the Extended Projected Profile (EPP) message. This enables ATC to evaluate the need for any further interventions in the aircraft's trajectory. If necessary, ATC can issue tactical speed adjustments to ensure safe separation and effective sequencing. With the enhanced speed intervention procedures under DYN-MARS, these adjustments are aligned with the aircraft's actual deceleration capabilities, enhancing more efficient descent profiles. The updated FMS functionality enables the vertical profile to adapt dynamically to such tactical speed interventions. This allows the aircraft to remain in managed descent mode, down to glide slope intercept, reducing the need for manual vertical path adjustments by the flight crew. Finally, once the aircraft is established on the glide slope, ATC may issue additional speed instructions, if necessary. However, with DYN-MARS, the impact of such interventions on fuel consumption and noise is significantly reduced. This process, a continuous, structured exchange of intent and response, offers a highly integrated solution that enables close coordination between the aircraft and ATC. It supports the reduction of fuel burn and noise while preserving current levels of capacity and safety.